That was part of our being able to not only guard against future failures, but to fully exploit what we were doing with the spacecraft. It didn't actually land in that giant crater. And just a little side note, when we first did our simulations, as you'll see in the next video here, if we could start that please, we were looking at the geometry of it and using a rather low-resolution map of Mars in the background. We actually didn't realize that crater would be in the line of sight as we looked at Phoenix, which landed well short of this crater. But here you see it, and in the up-close, high-resolution, you can actually see the shrouds of the lines and the panels of the parachute to give you the view of the detail that you're seeing. Now, in the next slide, once you get Phoenix down onto the surface, this is a color view of what you see. I'm going to have to give you a disclaimer here about the colors. Color balance is a very tricky thing. For our high-resolution camera, it has, in its color stripe, it has 3 channels, which you put together to get a color composite. You can stretch that to bring out details of the surface and such. Mars is basically red. It is the red planet, after all. And even when you look at it up close, it's varying shades of red. However, by stretching the color, you can bring out things that are reflective of different particle sizes, sand-sized grains or fine dust grains, or the composition of the materials, and that helps us understand what we're looking at. Phoenix landed on the vast plains in the northern lowlands on Mars. Not all of those areas were a good place to go. In fact, MRO ruled out an earlier site, which had the view that shows you those rocks, and you can see those by the shadows that are cast by it. Some of those rocks are several meters in size. You wouldn't want your lander either landing on top of that or landing next to it, trying to deploy its solar arrays as it was getting ready to do its own mission. So, moved it over to another area, but there's a scientific purpose here too. These rocks are scattered over a good part of these low-lying areas, which we thought might be actually the basin of an ancient ocean. And if the sediments that had fallen out of that ocean down on the surface, giving a very level plain, the fact that there are these boulders and rocks there is not consistent with that unless there's a process that brings the boulders to the surface after having been buried in those sediments. It's possible there are periglacial features here. We do know that on the Earth that the action, at least where you have liquid water and freeze-thaw cycles, can bring these materials to the surface. So this is something that we're still exploring, testing the hypothesis about whether there was once an ancient ocean on Mars. All right, if we go to the next slide, what we'll see here is some of the support that we did for the rovers still operating on the surface. This is the Opportunity rover in the Meridiani Plains next to Victoria Crater. And what you see here is one of the early shots for MRO when the rover was perched right on the edge of the rim of the crater, looking for, trying to decide which way it was going to move around. And this is what you could do. The orbiter gives you this picture of the surroundings, and you can plan your traverse of whether going left or right at these kinds of points. They were looking for a way to get down in the crater, and as we'll show in the video here, this is an artist's conception using the background image from MRO to zoom in with the computer to give you a rover's eye view and then an actual shot of it. So let's play the video for that part, please. It turned out that they were looking for a way into the crater. They went around the rim to the left here and eventually backtracked, going in just about where they had first approached it. But at least they knew that was the best place to go. Now, the Opportunity rover just turned over 10 miles on its odometer on the surface of Mars. And to contrast the different things that you try to do with the rovers and the orbiters, the orbiter covers that in about 5 seconds. So what the orbiter is about is coverage. What the rovers and such are about is getting down and exploring up close, in situ at those places, to see things that we can't see from orbit because perhaps it's covered by dust, perhaps the grain sizes aren't right for the wavelengths of the instruments that we're using. Whatever reason, we can use that as real ground truth for what we see from the orbit, and then we can extrapolate to other places that we've not yet landed at. The next slide shows us another factor that we do. I mentioned the weather camera that we have. We're actually looking at phenomena, clouds and dust storms in Mars, and trying to understand some of the layering that I'll talk about later. It's a mixture of ice and dust, and how that dust gets incorporated into the layers is one of the open questions that we have. Here we're looking at a local dust storm that's indicated by the white arrows, and you'll notice that in a day it had already traveled much closer to the MRO site, which is the Spirit rover down on the surface. Spirit at this time had a lot of dust on its solar arrays and was having trouble getting enough power from sunlight. Knowing that this dust storm was coming, they actually changed the operations they were going to do for the next several days to limit their need for power so that they could weather this storm as it came over the site, and reducing the solar absorption even more by the rover. So that's another aspect of what we do. But again, there's a scientific purpose to looking at the frequency and the numbers of these storms and how we move this dust around the planet, including into the polar regions. All right. Next, we're also going to, next slide, please. We're looking here, down in the rectangular panel there, you see an altitude scale. That is, how high are places on Mars? It's color-coded so that the blue areas are very low, the high areas are reddish. And you'll see an area that we call Tharsis, which is where the big volcanoes on Mars are. That's the reddish area. And then you'll notice these blue plains in the north and a great impact basin that's in the south, which is the Hellas impact basin. However, as big as Hellas is, we suspect that there's an even bigger one. That is the difference between the southern highlands and the northern lowlands. There's been two hypotheses that have been put forward for that. One is that internal convection of the mantle and crust has eaten away and thinned the crust, which is sunk and given the lowlands in the north. The other is that there was a giant impact that blasted much of that material into space very early in Mars history. But to be able to do that, you have to sort of remove the effects of Tharsis, which built up many hundreds of millions of years later. And we can do that by looking at the very precise shape of the topography, which we have from earlier missions, and from the combined gravity analysis from all the missions, including MRO. MRO is particularly sensitive because it's at a lower altitude than the other orbiters, and is much more sensitive to the bumps and mass concentrations in the Mars crust. So when you do that, what you see is over there is an elliptical basin in the polar view looking down on the planet, and that, we think, is the solar system's biggest impact crater. If this is true, this is the case, then the reason for the dichotomy between those southern highlands and the northern lowlands is actually an impact basin. This thing would be 8,000 kilometers across, about 5,000 miles. So, indeed, a big object, and we're learning about that. Let's go to the next slide, please. Now we're going to look at one of the areas that is showing us a lot of diversity in its composition on the surface of Mars, but it also helps us give you a feel for the scale that we're looking at the planet. In the upper left, where the white box is, that area is an area that's taken with our weather camera. And so you're looking at things at a spatial resolution of about half a mile or so on the planet. What we're going to do is take that white box, and in the upper right panel, that's the black box. Okay, so now we're going to a different scale here. We're going to zoom into that black box. If you look down in the lower left, you'll see that we're going to look at a particular crater. And the white box there is what we'll be looking at in the next couple of slides. But before we do that, let me tell you a little bit about the composition variations that we see. We're going to use false color as a way of indicating what we see and identify as mineral signatures. These are taken by looking at reflected sunlight from the planet, looking at the pattern of that reflection as it varies from wavelength to wavelength, and using that to identify that there, exposed at the surface, are different kinds of minerals. We're particularly interested in those that were formed by the interaction with water. And so we call those the aqueous minerals, and we're going to identify some of the locations where they occur using these false colors to indicate it's not just one set of those kinds of minerals, it's a whole variety. And there are implications to that diversity, which we'll talk about. So now let's go to the next slide, zooming in to that white box that you saw before. And now we're looking at the rim of the crater at the spatial resolution of our composition instrument, which is about 18 yards or so across for a given pixel projected down onto the surface. But it's looking in over 540 channels as a way of trying to identify, and color-coded here are different mineral assemblages as the function of depth and their exposure in the crater wall.